Hello, welcome to training for the M9195 Digital Stimulus Response Module. In this video, we will introduce you to basic concepts and functionality of the DSR module using the soft front panel. This video will be most beneficial if you have already watched the introductory M9195 product overview video. First, I'd like to start with a very simple example to get us up and running. I'm going to open up a very simple style file which can be opened with a common word editor such as Notepad or WordPad. In this case, you can see the various blocks that I covered in the lecture. Here's the signal blocks where we declare signal names and we associate a direction with that name. Next, we declare sites. We can declare various sites. In this case, I'm declaring a single site called my site. I'm taking the signal names as shown in the first column. I'm associating that with a physical channel and then associating that also with an ordinal in the case that we're doing a response readback. The next group is called the DC levels. I declare various DC levels for the signals within my pattern. You can see here V in high, V in low, V out high, and V out low. Keep in mind that the reference of the VN and the V out is with respect to the device under test. So you'll notice that the VN high and the VN low is the input to the DUT, which also instructs what our DIO module, what the DSR module output driver will drive to. So in this case, I'm driving a high level to 1.8 volts. I'm driving a low level to 0 volts. Likewise, the V output is with respect to the device under test, and at the DSR input, we're declaring threshold voltages for responses coming back. In this case, the high level will be anything at 1.4 volts and above will be recognized as a high, and anything at 0.4 volts and below will be recognized as a low. The waveform timing tables are declared in this block here. I covered how important that is in the lecture previously. Here I'm declaring pattern burst and pattern execs, which group the patterns themselves into a burst. You can organize multiple patterns into a burst, sequential burst, and then those patterns are grouped into a pattern exec, which associates the patterns with DC levels as well. And then I declare a simple pattern, in this case a single pattern called my pattern. I'm going to associate that with a waveform timing table, and then I declare my vectors underneath that. Now in this case, I have a loop block which will loop these various vectors shown here 4 times, and I can measure that with my LXI scope. So that's a very, very simple style file. It's just a text file. I'm going to go ahead and close that. And next I'm going to open my soft front panel for the M9195 DSR module. I do that by going to the Start button, Keysight, MDSR, and open the soft front panel. Now the soft front panel, as it's opening up, will recognize that there's one M9195 module in this chassis. It's in slot 12. I'm going to go ahead and connect to that, and it will instantiate a instrument session with that one module in there. I'm going to go ahead and load that pattern file or that style file that I just pointed to. So I'm going to select load files, and I'm going to point to the simple style example that I just walked through, and I'm going to go ahead and import that. When the soft front panel sees a valid style file, it will import it. It does syntax checking on that file, so if there was an error on the file, it would display an error here in the soft front panel. But very quickly we can walk through the different attributes that have been imported from that file. Here's my signal attributes D0 through D3 and a direction associated with that. Here's my site. The site is associating D0 through 3 to a physical channel that's on the M9195 and the ordinal associated with that. DC levels, I mentioned that before, D0 through D3. You can see V out low, V out high, V in low, and V in high were imported properly. The waveform timing tables, as shown here, the period is displayed in the upper left. In this case, it's 100 nanoseconds. And then the various signals and the characters associated with those signals, the events, and the time of those events as well. The pattern exec and the pattern burst are shown in the pattern tab here. And then finally, the single pattern that we imported is shown in the far right as in the patterns tab. If we had multiple patterns, this drop-down box would show multiple patterns here. So once the style file has been imported into the M9195 driver memory, we can go ahead and activate it, which pushes a compiled version of that down to the hardware itself. And then I can go ahead and initiate that, and I'll see my pattern showing up on the LXI oscilloscope. Now on this LXI oscilloscope, I've got logic channels connected, and I also have the analog probes connected as well. So D0, 1, 2 and, are connected to channels 1, 2, and 3 on the analog probe, so you can see both the analog and the digital display at one time. So in this case, very simple pattern, but what I've done here is I've got a loop. 4 times I loop through this pattern where you can see that the D0 on the far right hand side will toggle 1, 2, 3, 4, 5, 6, 7 vectors. It will be toggling, and then we'll go low for one vector state or one period, and it will do that 4 times. So if we look at the pattern here, we'll see a toggle 1, 2, 3, 4, 5, 6, 7, and then we go low for one state, and we repeat that 4 times. So you can see that running style files using the soft run panel is very easy and very quick, and it allows you to edit the files very easily. If I wanted to change this real quickly, I could go ahead and open up the style file. In this case, I'm going to open it with Notepad, and I can go ahead and change that at will. So say I wanted to add in a burst of ones here. Let's go ahead and change this. If I wanted to edit the pattern very quickly and have a burst of ones show up between each loop, I'll go ahead and implement that. So I've got 3 periods with a 1 state for all of the signals there. I'll go ahead and reload that last file, and you can see that it shows up under my pattern. I'll go ahead and activate that and initiate it. First, I've got to arm my scope. And now you see that I went ahead and inserted 3 1 states or high states on all of the channels using that edit that I just completed. Next, I'm going to show you a little bit more complicated example, also using a style file. I have one called example complex, and I'm going to go ahead and open that with Notepad. And as you can see here, I've got the same basic setup, but I've added a couple blocks in here. The signal groups block is a convenient way to organize bus structures. It's sort of a shorthand editing method here, which will tie channels D0 through D3 together into a single bus structure that's easy to reference. In this particular case, I'm setting up multiple banks here. Remember, we can support multiple sites by just declaring them in the site blocks here. I'm calling this bank 1, bank 2, bank 3, and bank 4. We come down here and we can declare also variables. One nice thing about the style file method of entry is we can declare variables which will be used to set periods and offsets for the voltages, and they can be used for some of the margin testing that I'm going to show you in subsequent examples coming along here. In the DC level block here, I declare my bus as applying to D0 through D3 in this case, and I declare input voltages as well as output voltages. And notice what I'm doing here is I'm also declaring an offset associated with that input voltage. I'll use those as we proceed with some of the examples a little bit later. In this case, I've declared multiple waveform timing blocks. Here's waveform timing block 1, here's waveform timing block 2. Waveform timing block 1 uses the variable I set up, which is called myPeriod. MyPeriod is declared up here at 50 nanoseconds. The characters that are declared in the waveform timing blocks are associated with actions. It's a little bit hard to read here, so let me sort of edit this, make it a little easier to see things line up here. And you can see that that we're declaring characters for D0, D1, D2, and D3, and these are multi-actions within the bit period. So in this case, the T stands for drive high at 0 nanoseconds, drive down or low at myPeriod divided by 2. Another case where having a variable is sort of a nice feature. Waveform number 2, waveform table number 2, is unique. If you take a closer look at it, you'll see a couple characters that you don't recognize. In this case, I've declared an A and B character, C and D, E and F, and J and K characters, and what they correspond to is events that occur not at 0 nanoseconds, but somewhere else within the bit period. So in this case, A and B occur at 20 nanoseconds. E and F occur at 40 nanoseconds, and J and K occur at 50 nanoseconds within the bit period. I'm going to use that later on in the example that I'm going to show you. We've got our pattern burst and pattern execs. In this case, I'm also showing you a new concept called macro definition files. So just like in programming, we can declare macro patterns here, which will be a block of patterns that will be used and inserted into another pattern that we're building. In this case, I'm declaring a simple pattern, which is nothing but, in this case, we're showing 5 different vectors, various levels within the vector. We do declare a different vector. It's called pass-in parallel vector. One nice feature of the style implementation for the M9195 is we can declare a macro pass-in vector that I'll show you how it's used later. When I pass in a vector value in my main pattern, it will import that into this pattern block here, and will activate that particular pattern. A pass-in serial pattern is very similar. When you see the pound signal in here, we can pass in a value that will populate this column in the pattern, which happens to line up with the D1 signal. Now this is how I use those particular macros. In this case, I have a pattern called simple pattern. I declare a waveform timing table of number 1, WFT1. I will go ahead and just output a couple vectors. Notice that the D0 is always toggling as I'm doing this. In fact, throughout the whole pattern, I'm going to toggle D0, and you'll see that in the scope when I run it. At this point, I'm inserting those macros that I declared earlier. So first, I insert simple macro, which will just be this block of vectors will get inserted right here. It's very simple. In this case, we're calling the macro pass-in parallel vector, and we're giving it a variable called mybus equals 100t. Now, mybus was that construct that I used before, which was the signal group, and I'm telling the macro to go ahead and insert the value 100t into this variable shown right here. The next macro is pass-in serial pattern, and in this case, I'm telling D1 will get assigned these values 001, 001, 00010, and that will be populated in the hash character that's shown in the center of the pattern here. This is very useful actually when building up serial protocol commands because they're passed in a serial method rather than a parallel or vector type method. The rest of the pattern here shows some interesting and valuable features that are available with the M9195, which includes changing the waveform table as we proceed through the pattern. So in this case, I'm going to change the waveform timing table to waveform WFT2, which happens to be at 50 nanoseconds. Let's go back and review that. Here's WFT2. I'm sorry, that's actually 100 nanoseconds. So we're going to pass in 100 nanoseconds. We're going to run these vectors at 100 nanoseconds. Then we'll run these vectors at 50 nanoseconds. So we're back to 100 nanoseconds, 50 nanoseconds. And finally, at the very end, we start inserting those special characters. You can see here B, D, F, and K. What that will do is it will retard the edge placement within those bit periods for the subsequent patterns that are generated. I also have additional patterns down here that I'm not going to talk about right at this instant because we're not going to use it for this demo, but we'll just run the one pattern exec. So let's go ahead and make sure we'll save that. We can close it, and then we'll go ahead and import that to the soft front panel. I'll load pattern file, and I'll select example complex. As I covered before, you can see that the attributes are all loaded in and displayed. Notice that there are multiple waveform timing tables here, so I can look at waveform timing number 1. That one is 50 nanoseconds. Waveform timing number 2 is 100 nanosecond period. And you can see here also the special characters that I defined and the events that are associated with them. A, B, C, D, E, F, J, and K, as you can see here. And the pattern itself shows up here. You can see the macros got inserted as shown here. Also at the very bottom, we're toggling between waveform timing tables, 50 nanoseconds, 100 nanoseconds, 50 nanoseconds, back to 100 nanoseconds. And you can see the special characters showing up in the pattern. So let's go ahead and we'll activate that site. And then we'll go ahead and make sure that our scope is armed for signal acquisition. And then we'll initiate that. And you'll see that the acquisition was made, the patterns were generated. And what you're seeing here is if you look at the very bottom, this is D0. And remember, I was dispatching a clock, or I was toggling high to low throughout the pattern. And you can see here that this is waveform timing table number 1, which runs at 50 nanoseconds. This is going back to number 2, back to number 1, number 2, number 1, and number 2. So you can see how the timing table seamlessly changes in the middle of the pattern here without any glitches at all. Let's go ahead and look a little bit further to, let me offset this just a little bit, 1 microsecond. See if I can get to the end of this pattern here. Let's set it up for 2 microseconds. And if you look closely here, it's a little bit hard to see. Let's try 3 microseconds, and then we'll go ahead and expand this out a little bit here. If you look here, look closely, you'll see the clock edges at the very bottom here line up with the periods itself. So we toggle high at 0 nanoseconds of the period, and then we go low at 50 nanoseconds in this particular, I'm sorry, 25 nanoseconds. No, this is waveform timing table number 2, which is 100 nanoseconds period. So this is 100 nanoseconds from rising edge to rising edge, and the falling edge is at half the period, which is 50 nanoseconds. What you're going to see is starting with this edge right here is lined up with the, and this happens to be waveform timing table number 1. We go to waveform timing table number 2, and you'll start to see that the rising edge on the green trace is being retarded or slowed down just a little bit by a certain amount. So we've got 20 nanoseconds, 30 nanoseconds, 40 nanoseconds, and by the time we get to the last high state here on the green trace, we've delayed that by as much as 50 nanoseconds. We actually line up with the falling edge of the clock. So this shows the effect of the cyclizer in the M9195, which is a very powerful feature as far as our customers setting the edge placement for these various patterns. I'd like to show you one additional method that you can use for entering in pattern information into the M9195. During the lecture I talked about the OpenXML, which is really the Excel style format of a file that we can use to enter in all the information that I showed you with the style that I used with the style file. At the very bottom of the spreadsheet you can see the various tabs here: Signals, Site, DC Levels, Waveform Table, and Pattern. If we walk through and look at each one of these tabs, you'll see that we're declaring the same information that we declared in the style file. The Signals tab will declare signal names and associate a direction with that. It also defines a signal group. You remember seeing the signal group in the complex example as shown here. The Site tab will associate the signals to physical channels as shown here, as well as ordinals in the second column here. One nice thing about the Excel examples is we do have the space and the luxury of putting in more documentation into the Excel spreadsheets. So it's a little bit easier as far as usability goes. The next tab is DC Levels. You can see here that we're declaring both VOUT and VIN levels for D1 through 4 as shown here. Waveform Table. So this information is the same information that's in style. Waveform Table as far as the characters and the association of the symbols to the characters, as well as the events that occur and what time they occur within the bit period as shown here. And finally, the pattern itself. In this case, again, it's a very simple pattern. But we declare D1, 2, 3, and 4, the signal names here, and the columns are the patterns that are going to occur at runtime. So we simply just have to save that as an Excel file, and then we can import that using the soft front panel. So let me go ahead and go back to my test machine here, and I will go ahead and load the pattern file. In this case, you'll notice that the pattern files that will recognize the .style, .sti, .xlsx as shown here. So we're going to go ahead and point to the OpenXML file, which is the M9195 simple Excel example. I double click on that and it imports that information into the M9195 driver memory space. Once it's in the driver, we can inspect it just like we did before, and you can see that the values are all present here in this Style Components View window. And I can go ahead and activate that and run it just like I did with the style example. And you'll see that the pattern is generated just like I did previously with the style example. Now, the Excel file format is convenient to use, and for some customers it may end up being a more convenient editing tool to use. Thank you for watching this video. Following videos will show how the M9195 IVI driver is used to program the DSR.